Okay, so thanks a lot for the invitation, and thanks for the opportunity to share like the chemist perspective on the development of self-assembled monolayers and also known as SAMs. Let's do this. So yeah, so nearly a century ago, Paul Dirac made a really nice statement that captures the essence of the chemistry. In 1929, in his paper called Quantum Mechanics of Many Electron Systems, he wrote that the fundamental laws necessary for the mathematical treatment of large part of physics and the whole of chemistry are thus completely known. And the difficulty is only that the exact application of these laws leads to equations much too complicated to be solvable. And here I am, almost 100 later, still calling myself chemist and working on the systems that are too complex to be solved analytically. With my today's talks, I would like to touch on the question of the molecular design, and specifically like how much of it can be actually called rational and how much is just a pure luck. And the object of my presentation will be the small molecule and the so-called whole selective self-assembled monolayers, which recently became popular choice for both tandem and single junction perovskite and also organic solar cells. So I will try to walk you through the rational steps that we made to come up with this idea, and I will leave it up to you to decide how much luck we had in this project. First let's talk about the development of the SAMs. So let's start from the prior art. When we started working on the whole selective materials for the perovskite solar cell, the king of the field was spirometad, and maybe some of you know that in principle this was one of the major breakthroughs that enabled the initial perovskite solar cells when the liquid electrolyte was changed to the solid state electrolyte. However, there are some issues with this material that are quite known. One is the price. Even though it's very widely used and there are like a lot of suppliers on the market, so in principle the price should reduce, it still stays quite high, possibly due to the relatively complicated synthesis. The other problem is stability. This is example that at high temperature spirometers can crystallize, which leads to the reduction of the long-term of the performance, and it's quite a common practice, for example, in the field, to change the spirometers with PTA when you go to the stability measurements, especially at the higher temperatures. So these two factors are really widely discussed, and this is like well known to everybody, but there are some additional issues that were specifically important for tandems. So if we go to tandem configuration, the perovskite cell is deposited on top of the silicon solar cell. It means that the light first have to pass through the spirometer and only then reach the absorber layers. And if we look at the EQE curve and compare it with absorption spectra of the both pristine and oxidized spirometers, we can quite clearly see that there are the same features. So for the pristine spirometer, we see the feature at 400 nanometers, and it's here. So we lose absorption, lose light here. Then the second feature from the oxidized spiro is roughly at 500, and we lose it here. And then even this minor feature, we can still see it here in the EQE spectra. So it's clear that we lose a lot of useful light to the spirometer, and it clearly has to be reduced. So that was our initial goal, let's say. So we need ideal whole transporting material for tandem, specifically for tandem solar cells. And so apart from the usual requirements such as energy level, stability, price, and many others, there are like two additional challenges. So there should be no parasitic absorption, as I already mentioned. And the second is also compatibility with textured surfaces, and this is one of the key factors for the high efficiency tandem architectures. Now, thinking as a chemist, like what strategies could be to reduce the parasitic absorption? Okay, the first one, we need to actually reduce absorption of the material itself. So the clear advantage here is that, okay, we leave everything the same. We don't need to optimize the architecture, the position, we just try to make more or less similar spiral, which has slower absorption. So this is clear advantage, but on the other hand, while it seems quite straightforward, it's very hard, because to reduce absorption, we need to reduce the conjugation. And well, if we reduce the conjugation, then we also reduce the whole transporting ability of this material. So there are like benefits and drawbacks to this approach. Another option, let's switch to inorganics. And yeah, in organics, materials are quite often associated with a good stability, low cost. But in practice, like anyone who worked with copper thiocyanate, for example, which seemed to be very promising for these applications, the reproducibility is extremely low, and it's really hard to work with this material. The reasons are not entirely clear, but I think it's somehow diminished, like, and not many people work on that anymore. And the third one, quite interesting also, like, and quite obvious one. Well, if our layer absorbs too much, then let's just reduce the film thickness, and it naturally absorbs significantly less light. And also, what is also another advantage of this approach is that also, if we reduce the thickness, we also improve the charge transfer through this film. Simply speaking, charge carrier has lower distance to travel from one layer to another one, means it has less time to recombine, and also it leads to a lower series resistance. So we can avoid use of doping, which, as you have also seen, leads to parasitic absorption. So this is an interesting approach. And the advantage of this approach was actually demonstrated for the PTA and PIN devices. So when the thickness of the PTA was reduced by changing the concentration and the solution, the fill factor was significantly improved. However, that came at the cost of the reduced VOC. So there is some kind of optimum thickness where we reduce the resistivity, but we still don't get the problems with the VOC. And the problem VOC quite easily can be associated with the incomplete coverage of the substrate, because the film becomes just too thin, and there is like any substrate has its own roughness. So we reach the situation when there is some non-uniform coverage. But the message of this graph is actually quite clear. So go as thin as possible while maintaining the full coverage of the substrate. So as thin as possible in organic chemistry means basically single molecule. We cannot go thinner, because that's it. We lose the integrity of the material. And if there are more than one molecule, then it's already inherently thicker film. And luckily in organic chemistry, there is a way like to achieve ultimately thin layer, because certain molecules that have the ability to spontaneously form self-assembled monolayers on specific surface. And to do so, the molecule needs basically two key components. So the first component is the head group or anchoring group. There are various names to that. And this group has to have specific chemical interaction with the substrate that we are going to use. One classical example is thiols and gold. So if we have SH and we have gold, then some dynamic bonds are formed, and it can quite nicely form a monolayer on top of that. Now the second component is the functional group or functional fragment, which is attached to that head group. And the function can be, in principle, whatever we want, but also important that this fragment is not interacting with our anchoring group. So this leads us to self-terminated process. It means that once the anchoring group attached to the surface, that's it, the process stops. It cannot form the second layer because there is no interaction here. And so our idea was quite simple. Let's use this natural self-assembly process to create the ideal whole transporting material for tandem solar cell. Well, it's easier to say than to make, but this is how we approach this thing. Yeah, so let's return to the molecular design as a concept. So how do we design the molecules? And when we design new molecule, there are basically two key considerations. So one thing is what we actually want to achieve. So we already described what we want, what properties we want. We want it to be how selective, we want it to have ability to form monolayers. But then you also have to think about what is actually possible to synthesize. So we cannot build the molecule from scratch from the atoms. So we always have to think like what is possible, what is available, and this also links to the price of what can we buy and what can be what can have reasonable prices. So, and this is where experience play kind of a crucial role. So the more you have experience, the easier for you is to navigate between idea and reality. So how we dealt with that, so this is an example of one of the compounds that we came up with, design. So we just looked at the existing whole transporting materials. This is example of V886. We also looked at spirometad. And then the question like how can we introduce into this structure the functional group? So this specific example, we limited ourselves to the fragment that is actually responsible for the whole transporting properties. And then all the rest of the molecule is basically just there for the morphology, because again, like if we use it as a classical HTM, film forming properties are important, aggregation is important, crystallization is important, but we don't care about that anymore like here. And then we can take, then we have the place where we can introduce something, and then we try to introduce phosphonic acid functional group, which is quite good anchor. It does not necessarily has to be phosphonic acid, but there are not so many like classical examples of the groups that can form self-assembled monolayers. Yeah, and so basically we have this modeling starting compound, which is called V1036, which combines these two functionalities as we planned. And yeah, on paper it's quite nice, but in reality, these ideas that let's just combine two different functional fragments and let's make it work, quite often these ideas don't work. And like just simple example, if you add wings to the car, it doesn't make the car flying. So in this case also, like you expect them to behave in synergy, but in reality quite often they might interfere with each other. So there is always this uncertainty about how well they will behave once put it into a single molecule. And then so we had this material, and this is like some part of the story that I think never was told, that our initial idea, because I showed you our starting point, so NIP device on top of the silicon solar cell. So our initial idea was to use it instead of spirometad in NIP devices. And thanks goes to Felix Lang and Lukas Kegelman from HCB. So this is the result that they obtained. So red curve shows us the result when there is just nothing at all. We just have perovskite and we deposit gold on top of that. We still get some VOC, but the performance is really bad, and obviously this device cannot work well. But then with V1036, you can see that there's some improvement. VOC is still rather low. JC is also limited to factor is not great, so it's roughly 4 to 5%, but it's something. So in principle, idea is there. Yeah. We got some changes, and also we did it with different materials. Also we see the variation, so it means that something is happening. Our process is not making it even worse because it was already really bad. But yeah, something is happening. But then if you think about practical problems, so we are not happy with 4 or 5%. We wanted to be like at the level that is competitive. And then we had a lot of discussion. There are like several rounds of optimization for that. But in reality, like what problems we encounter. So first one is the position of the top contact layer on top of a monolayer. So monolayer is not very, hard material, so if we have gold, it definitely can migrate through this monolayer. If we use some oxides, then also like it might be harmed during the deposition process, and so on and so forth. So this is one problem which makes it really difficult to realize, let's say, good contact in terms of technology itself. And then the second is more related to the Perovskite and monolayer. So far, even now, like still, we don't fully understand the surface of the Perovskite, and because it's quite often a mixture of various cations and ions, so it means that the surface termination is quite undefined. Also, Perovskite is kind of soft material, so if the molecules are too small, then you can move inside of the Perovskite and so on and so forth. So it means that we also don't really understand how to make a good monolayer on top of Perovskite. And so these two problems were kind of critical, and this project was put on hold. So we still have not achieved this goal of changing the spiral in the NIP devices. But then later on, like after something like a year almost, two papers that were important for the development. So first paper that got our attention was published in Science, so from the Brabitz, Snade, and Halik groups. And the paper was focused on the HTMs actually, so this was the main story of the paper. But then if you look at the SEM, and then if you look at the formation of the layers, you see that they use something that is C60 SAM. And in this specific paper, they did not explain it very well, but there was prior paper describing exactly this thing, how titanium dioxide was changed with fullerene-based SAMs. Device performance was quite nice, and in this case, remember these two problems that I told you. First one is the position on top of the monolayer. In this case, it's fine because perovskite is deposited by solution processing, so solvents cannot harm monolayers because they chemically attach to the surface, so you cannot kind of wash it away. So it's there, and it's soft enough so that you don't get any harm to your monolayer. And also the second problem about the interface of about the monolayer, formation of the monolayer. So also if we go to ITO phosphoric acid, this is much well-studied system. So this is where we switched from NIP to PN, and we used exactly the same materials, and we got already, like from the second batch, we got really good device performance with V1036. It was good, so it was proof of concept that these concepts can lead to quite nice performance, but still there are some questions like how do you make it better than PTA? So again, PTA was not the perfect HTM. And okay, so the first kind of thoughts that we had, maybe this molecule, this layer is already like too thin, and we go into tunneling regime or something like that. It means that we lose selectivity and it's not acting like so well as a selective layer. And well, chemical solution to that, let's just make bigger molecules. So this was what we had in hand more or less, and we were able to quite rapidly prepare that molecule. And then the second problem that might happen, just idea, it's not necessarily true, but that the molecules are more or less too big. So we had this carbazole with substituents, and then there is only small phosphoric acid that is attached to ITO. So in principle, maybe they cannot form a dense monolayer on top, and this leads to loss of selectivity to some additional recombinations. And the solution to that, make smaller molecules, so exactly opposite. And for that we did two molecules initially 2-pax and neo-2-paxy. And well, long story short, this material did not show us good performance. It was VOC limited, so performance was roughly at 14% level. And it's still not clear, like, you know, like if you have this idea, it's not clear is the idea is not working, or if it's just this specific material that is not working. So maybe making them thicker will be better, but not with this material at least. However, with the smaller molecules, we managed to, for the first time, to achieve the performance that was better than that of the PTA, and without any additional interlayers or treatments. So that was really exciting result. Now I won't go too much into the details about this works because there was very nice presentation by Amran Al-Ashuri on this on this PhD postdoc series. So those of you who are interested in especially physical characterization of these of the devices of these materials, you can have a look at the on the YouTube. Now I told you that ETMs were first and HTMs just followed them. So then the question, why HTM sums are so popular and ETM sums are not? And this is one of the hypotheses, but this is the this is from the publication the synthesis wrote to get one of these C60-based phosphonic acid SAM material. And as you can see, the road is quite long, and especially if we compare it to 2-PAC-Z, it's clear that these molecules are significantly simpler. And also if we compare the starting compounds, even assuming that, okay, we maybe can buy some intermediate compounds, but still, like if we look at the chromophores at the starting materials, so C60 is usually hundreds of euros per gram, and carbazole can be bought at less than euro per gram level. So that was one of the reasons. And then the second was, I guess, quite rapid commercialization. So already with the first publication, the 2-PAC-Z, because of their simplicity, they were commercialized first by Tokyo Chemical Industry, and then also the license was acquired by Dynamo, American Perovskite, and the latest one was Siva. There are also companies who sell it without license, but I won't advertise them, so don't buy from them. Okay, and now, you know, like working in this field, we always get this question, like, is it a really monolayer? Like, how do you know that? And is it like, so how do you explain this? But then I have one of the implications that if we think about these materials as forming monolayer, if we make this assumption that this is true, then there are many things that we can do. And one example is mixed monolayers. If we use conventional HTMs such as spirometad or PTA, imagine that you add some random molecule in amount of like 20% or 50%. Well, most probably it won't be anymore a whole selective layer, because you won't get any charge transport through such mixture. However, because SAMs are two-dimensional, if we make mixed monolayers, then we still have areas where we have our whole selective material, and then all these additives, they act as just additional bridges or whatever function we want from them. So this adds additional, additional dimensions for the optimizations, and especially in terms of some minor tweaks. So once you have a good material, you can really fine-tune the properties if you want to. And this is just like a small example. Problem with ability. Those of you who were working with Me4Pax probably know that wettability is really bad. So it gives slightly better efficiencies than 2-PAC-Z. This is quite reproducible. However, people were struggling to reproduce this material for a long time because of the poor wettability. And it's really, it seems that it's really a border case, because it really depends on many things, on the roughness of your substrate, on the supplier of your ITO, on the cleaning procedure. And in some cases, it's hard to make films, but possible. And in some cases, it becomes impossible to make the film. And again, like if we think about it as a monolayer, we assume that it has at least some orientation on the surface. It means that on the top will be the parts of the molecules that are here. And in case of Me4Pax, we have CH3 groups that are non-polar, and perovskite solution is polar. So it means that we have bad compatibility between these two materials. So how to solve these? Yeah, and if we make devices out of that, so that was my batch. Like, you still can get working devices, but the amount of shunts is just like devastating. So you get significantly more not working devices than working devices. Yeah, so how to follow like purely geometrical considerations. I just went to the catalog and looked at all the phosphonic acids that are there. And yeah, we need to make it more polar. So one of the molecules that was commercially available was diphosphonic acid. The size of the molecule is more or less the same. We can compare it. just easily counting the number of the carbon atoms. So it should be also on the surface. And yes, indeed, like if we look at the number of shunts, yeah, we had significantly reduced the number of shunts, and only those that are more or less like from the dust, they're still there because dust is everywhere, but you get significantly higher output of the devices. And yeah, like how this relates to, how this transforms to the properties of the monolayer. So all these results, they are shown with a 20% of this additive or mixture, and 20% of hexylene phosphoric acid and B4PEX. If we just look at the contact angle, this is Perovskite solution. If we just drop on top of the of our monolayer, it's kind of strange to see because, well, wettability in both cases is kind of okayish, and the difference is not huge. However, we have seen that in terms of output, in terms of shunted devices, the difference is huge. So that's the dynamic nature of the spin coating. And we also try to look a bit deeper. So our hypothesis was that there are polar groups on the surface of our monolayer. So we tried to make this like more detailed characterization where we look at the both polar and non-polar dispersive parts of the surface energy compounds. You can do this by using different solvents, and this type of representation is called wetting envelope. So indeed, like this polar part, there was not a huge improvement, but it was enough like to lead to significantly closer like to 0 degrees than in the initial case, and that's quite a nice look at how can you tune the surface properties of your monolayer. And especially this might be relevant for the large area deposition by the solution processing. So you can really choose if you want to have it like more wetting or less wetting, depending on your process. Yeah, and just to some device results, we try to compare like if it works in two parts of the world, in the United States and in Germany, and yeah, it was fine. So with different perovskites and different baseline protocols, and the addition of hexylene phosphoric acid did not have a strong impact on the device performance. And I also tried to scale up the devices just more or less for fun, but it was quite nice. So 1 square centimeter devices performed quite well. Okay, and now I guess it's time to continue to the discussion. So yeah, I told you some stories about molecular design, and well, ideally we want it to be as rational as possible, and we want to reduce the slack element. However, there are many questions like always happening there, to which we still don't have like clear answers. And our latest try kind of to look and to link the properties of the molecule to get the predictive power to the molecules. We try to analyze the largest set of the molecules. So this is like 9 SAM-forming molecules with quite small differences, so that to keep it like as similar as possible. And you know, like in medical, especially in medicinal chemistry, the screening approach is quite often used when we don't understand everything. So we just try to introduce some small changes into the structure and see how our system responds. So we thought maybe we could apply this also here. And I would just show like one graph, more like to stimulate the discussion. So if we look at the small subsets, this is comparison of ionization potential, which is the property of the monolayer and material itself, which can be easily measured, and also try to computate with fill factor. So if we look at these small subsets, what we can see is that, okay, there seems to be trend, and here also seem to be correlation, and in this case also. But if we just put everything on the same graph, what we lose predictive properties. So we have quite a wide range of ionization potentials, and the materials with the same ionization potential can have quite different values. And this is quite common in the field. We also do that if we have small subset. It seems that there are some correlations, but if we move to bigger picture, then these correlations are quite often lost. This raises the questions, how do we further develop these theoretical background, let's say, for these materials. And the last message before discussion, so in the recent Perspective in Science, there was like one sentence that I would like to quote. So how or why they work so well is still not clear. So this is for you to think about it. And with that, I'd like to thank you all for your attention and thank all the collaborators who contributed greatly to this work. Thank you.